Okay, next we need to define a partition because this is a part of Bayes' theorem. It says that you have to have a partition. Well, a partition, and this is the wordy math definition that you're seeing here, but it's a set of events in your sample space such that exactly one of those events occurs when the experiment is performed, and that the intersection of any pair of events is the empty set and the union of all of them is S. But in like more layman's terms, if I wanted to, let's say, partition this rectangle, what it means is I'm going to divide it up into pieces such that none of those pieces overlap each other, but if I add all those pieces together, I get the whole rectangle. So what happens whenever we're doing our experiments when we have these tree diagrams is that all those branches basically make a partition. When I add them all up, I get the entire sample space, but none of them actually intersect each other. They're all mutually exclusive. Then we have Bayes' theorem. Bayes' theorem holds as long as you have a partition, and we've been showing by using these tree diagrams in all of our examples that these really are partitions, so we know that this is going to hold. Now, I'm not going to read that giant formula for Bayes' theorem to you. I know it looks very intimidating and scary, but it's really not. So what I want to focus on are my notes. So Bayes' theorem is used when you're trying to find the probability of an event on one of the leftmost branches given the occurrence of an event on a rightmost branch. So you're going to do these by making tree diagrams, and you're going to make sure you label your branches as you work so you know what you've got and what you're looking for. So going back to example 1 with the soft drinks, notice that we have the original P of the machines, right? We have the probability of being on any one machine. And then our second branches are the probability of either being defective or not defective given which machine it came from. So what Bayes' theorem is going to help us calculate is what if we want to do one of these conditional, like what if we wanted to do something like this, but in reverse? What if we wanted to find the probability that the bottle came from machine 1 given that it was defective? What if we want to find the reversal? How do we find the other way? That's what Bayes' theorem helps us to do. And that's actually the question that we want to answer here is, what's the probability that the bottle came from machine 1 given that it was defective? So first, I just wrote down the giant Bayes' theorem, which says if I want to find this probability of M1 given defective, then I have to multiply the probability of M1 times the probability of defective given M1 over all of these different values down here on the bottom. Now, reducing, like what is all of this nonsense, or what is that? What does that mean? Those are basically the partitions that create the probability of D. Okay, but look, we already did that. We were able earlier in the notes to calculate the probability of D. We've already done that crazy looking formula that's in the denominator of Bayes' theorem. All that was saying was do your multiplications of your branches that all end in D. Take the probability of M1 times this direction's conditional probability, and I'll get this value. And then take my next branch and multiply it out, the one that ends in the D, and get this value. And then take my last branch, multiply it out, as long as it ends in the D, because that's what we want, get that value, add them all up. So we've already done this. So the denominator, that big crazy looking denominator, is nothing new. It's nothing that you don't already know how to calculate. All that's saying is saying take this branch that ended in D, multiplied by this branch that ended in D, multiplied by this branch ended in D, which gives me the entire probability of D on the bottom. Okay, so what, and you've already also calculated the top, so we know that the bottom is 0.004. Notice the top is just the specific branch in question. It's the branch that came from machine 1 specifically to defective, because that's what's in question, is what's the probability specifically that we came from this machine given that we ended up defective. So again, you've already calculated this value. It's 0.0002, or I guess they did it for us. 0.0002. And if you divide those out, what you should get is 0.05 or 5%. So although this formula looks very large and very scary, if you draw out your branches and if you label them, then you already have all of the pieces. You put the particular branch in question, the one that you're trying to work backwards to, over all of the branches that end in the correct place added together in the denominator. And that sets you up with your Bayes theorem. So let's do another example where we use Bayes' theorem. In this one, it says a factory employs workers on 3 shifts. The first shift employs 40% of the workers, the second shift 35%, and the third shift 25%. The absentee rate of workers on the first shift is 1.5%, but increases to 4% on the second shift and 12% on the third shift. What percentage of the absentees are assigned to the second shift? Okay, in other words, what's the probability that an employee is on the second shift given that they are absent? Draw a tree diagram and use Bayes' rule. So, let's see. First things first is we have 3 shifts. We have the first shift, second shift, and third shift. So my first branches have 3 branches each. The probability of a person being on the first shift is 0.4. Probability of being on the second shift is 0.35, and the probability of the third shift is 0.25. Now, on any given shift, you're either absent or you're not. So I'm going to call my next branches A and A complement for absent and not absent. Okay, so if you are on the first, so this is the probability of being absent given that you are on the first shift, that is 1.5% or 0.015. And look, I'm only going to label the ones that I'm interested in. Since I know that I am interested in the probability that they are on the second shift given that they are absent, I'm not even going to worry about labeling my non-absent branches. I could if I wanted to by subtracting, but I'm not going to spend time on that. So the next branch I'm going to label is what's the probability of being absent given that you're on the second shift? So that is 4% or 0.04. And finally, what's the probability of being absent given that you're on the third shift? That is 0.12. So look, all of our branches that end in absent are what we care about. So let's see. Let's go ahead and multiply them out. So the probability of being on the first shift and being absent is 0.4 times 0.015. I'm not going to actually multiply that out yet. I'm just going to set it up. The probability of being on the second shift and being absent is 0.35 times 0.04. And the probability of being on the third shift and absent is 0.25 times 0.12. So here's how Bayes' theorem works. The probability of, given that going the other direction, the probability of being on the second shift given that you are absent. So notice it's the opposite of this. It's not the same. That is equal to this branch's intersection, because that's the one we're specifically interested in, the 0.35 times 0.04, over, and then you add all of these 3 up. So over 0.4 times 0.015 plus 0.35 times 0.04 plus 0.25 times 0.12. So So we add up all of the branches that end in A for our denominator. Okay, that equals, I'm going to do a little bit of this math calculating quickly for us. Let's see, the top, if you take 0.35 times 0.04, you should get 0.014. And then if you multiply and add across the bottom, that should all come out as 0.05. Feel free to pause me and do that to double check. And then dividing that out, you should get 0.28 or 28%. So again, although Bayes' theorem looks really complicated, if you will just draw out your tree diagrams and label each one of them, it really is not as complicated as it looks. You take your particular branch that you're interested in over all the branches that end in the appropriate way, added together, and there you go.